And so let's continue. So where we are, first of all, you remember we are in the process. No, actually, we are no longer in the process. We almost switched from the vector quantities to scalar quantities. You remember, in an attempt to simplify our life in terms of calculations, right? So you remember, we replaced vector quantities with scalar quantities, right? So instead of force, which describes interactions between two charged objects, since that force is conservative, we introduce the potential energy. Again, energy of interactions, right? And then in the previous class, instead of electric field, which is again vector quantity, we introduce the scalar quantity, the electric potential. So now if you have an electrical aura created by some charge system, you can describe it either using electric field or using the electric potential. Okay, but now logical question, right? So since both of these things, electric field and the electric potential, describes exactly the same, there must be a relationship between them, right? There must be some connections. So today we're going to spend the whole class establishing bridges. So how can we move, for example, from the electric field to the electric potential? And how can we move back from the electric potential to the electric field? For example, why do we need this? Because most of the time, at the end of the day, researchers want to know the electric field. Let's say, for example. All right, and you have a complicated system. So if you start calculating electric field directly, it can be ridiculously painful. So instead of that, you can just move to the scalar potentials, calculate, for example, the net scalar potential of your system, right? Which will be easier. And then only you can move to the electric field, because in your applications, let's say, you want to know the electric field, right? So for example, some hypothetical situation. So you have to be comfortable moving back and forth between these two quantities, right? Because they're very, very important in the world of electromagnetism, right? Okay, so as I said today, the whole class will be about, what are you chatting about over there? All right, establishing these connections, right? So let's start with the first one. Let's assume that you are in the world of electric field, and you want to move to the world of electric potential. So how can that be done? Okay, for the last couple of years, I usually use the whiteboard to derive it. But now I want to move a little bit faster, so I decided to use slides, right? So the goal is to establish the bridge between the electric field and the electric potential, moving this way. Right? Okay, so a little bit of derivation. Derivation is simple, consists of like 2.5 steps. And why I don't want to skip it? Because in this derivation, we will use some fundamental things from the past. And it's good to sort of recycle them. It's good to use them from time to time. Then it's easier to remember them. Okay, so let's imagine that we have some completely arbitrary point charge here. Yeah. Can be positive, can be negative, it doesn't matter. And let's assume that this charge moves, or we drag it, it doesn't matter, from some initial point to some that arbitrary point, right? So it moves. And so, of course, so let's assume that it's exposed to some electric field. If there wouldn't be if there were no electric field, there wouldn't be anything to discuss, right? So let's assume that there is an electric field. Okay, of course, there will be electric force acting on the charge. And so let's try to calculate the work done by the electric force. Let's calculate work. And definition of work from physics 1, it's one of the points. So just to refresh again, just to refresh the expression for the work. Okay, so work done by the electric force, it's a dot product, integral of a dot product force dot ds. And from the initial point, you see the lower limit up to the final point, upper limit. Right. Okay, so now you remember what we want to get. We want to establish the relationship between the electric field in the electric potential. So basically, somehow we need to get into this expression electric field and the electric potential. For example, how can we get the electric field into this expression? Electric field is more or less obvious because electric force in the electric field are directly connected through the charge, right? You remember F equals QE. So electric field most likely will appear on this right-hand side of the equation. Okay, then how can we incorporate into this equation the electric potential? So it looks like we must somehow bring it to the left-hand side. How? Let's recall another expression from Physics 1. And actually, we already used it in this semester, right? So, yeah, that is ds, right? Infinitesimal small displacement as we move the charge. So, back to the expression. You remember work done by a conservative force as an object moves from initial to the final point equals to the negative change in the potential energy. Basically, delta U, it's a U final minus U initial and minus in front, right? You used it in Physics 1 and we used it 2 classes ago when I derived potential energy over charge inside of the capacitor. I used this expression. Okay, so now work equals to minus delta U, and of course you remember that the potential energy and the electric potential are directly connected also through the charge. So that's how we're going to bring the electric potential into this expression. Okay, so now instead of work, I will write minus delta U. You see, W equals minus delta U, but I moved minus to this side. So now minus is next to the integral, right? And of course, force is QE. And of course, charge is constant, so charge can be taken outside of the sign of integration. Okay, so now we have electric field. That's what we wanted. So and now we need to construct electric potential on the left-hand side. How? Definition of the electric potential, it's a U divided by Q, potential energy divided by the probe charge. So if this is true for V, then of course exactly the same we will have for delta V. Delta V will be equal to delta U divided by Q. So if I take this charge Q, move it to here in the denominator, we'll have delta U over Q, and that's delta V. Basically, derivation is done. So delta V, it's a delta Q over a delta U divided by Q. And it's equal what's left over here, integral with the minus. That's it. So that's the derivation. Right? As a result, we have an expression which we are going to use from time to time. And again, what it gives us, it allows us to go from the electric field to the, actually, we're not getting electric potential, we're getting a change, a potential difference, right? So you see integral from the initial point to the final point, and from the initial to the final point, and we're getting the potential difference between final point and initial point. So that point is at potential V final, this point is at the potential V initial, right? So basically, as I said, 2.5 steps of derivation, right? But at the same time, we have refreshed idea of work, this expression, and the relationship between the electric potential energy and the electric potential. Okay, strictly speaking, this integral is far from being trivial. It's a line integral. It's a calculus 3. But you know, every time in this course we find some tricks which can be used to skip integration. Right. Okay, we're going to do the same over here. Right. Okay, so which trick? I will just take it, copy and paste on the next slide. Yeah, here. Okay, so dot product E dot ds. Of course, we know how can we write that explicitly. It's a E cosine of theta and ds. Oops. Minus E cosine theta ds, where cosine theta is the angle between vector E and the vector ds. And then what is E times cosine? It's a component of the electric field along the direction, along the S direction. component of the electric field along the S direction. On the previous slide, we saw it, right? Okay, so it will be negative integral ES ds. And now you remember calculus. What's the graphical meaning of an integral? Graphical meaning of an integral. If you plot integrand, in this case E sub s, or E cosine theta, versus the variable of integration, in this case s, and that's what I have on the plot, you see? Integrand versus the variable of integration. Between initial and the final point, you see initial point, and here we have final point, right? So graphical meaning is just an area. Area under the curve. Integrand versus the variable of integration. So, and that's what we're going to use. In all our problems, of course, this curve is going to be much nicer, just straight line. And every time we will be calculating area over a rectangle or a triangle, right? So, which is very simple. So instead of taking a line integral, we're going to calculate area. But don't forget about this minus. It's a very, very common place for a mistake. Lots of students, sometimes even good students, forget about that minus. Once I remember, I even forget. Okay, not even, I forgot also. So minus integral. So it means that calculate area and add minus in front. So area, negative area. And another thing, in your homework, you're going to have a curve which part of the curve is above this horizontal axis and part of the curve will be below horizontal axis. So when you calculate area, that part which is above the horizontal axis, of course, will give you positive area. And that part which is below gives you negative area. So of course, you will have to subtract those areas in order to get the total area. Right? So be careful. Right, so that's what we need to do. So that's what, and again, it gives us change in the electric potential. It basically means V final minus V initial. It doesn't give us the value of the electric potential at a certain point. Every time it gives us delta V. Right. Okay, so that's what we need. And so I think now it's time for me to look at the example. I will probably switch to the whiteboard. And then after that example, there will be a question for you, and then we will start moving back from the electric potential to the electric field. Let me check. Yeah. So now it's time for me to switch to the whiteboard and look at the example. So what do we have here? The plot, x component of the electric field, and units you see now volts per meter. It's the same as newtons per coulomb. You can easily prove yourself by yourself, right? So newtons per coulomb, it's the same as volts per meters. Right? So electric field along the y-axis, vertical axis. And here x. So 2 meters, 1 meter, 2 meter, right? And the value of the electric field at point 1 is 1000 volts per meter. So what we need to get? We need to find how the electric potential changes with x. We need to get the function. We need to get the function. Again, you see what is given. We have information about the electric field. Right? So we have information about the electric field, and we want to get information about the electric potential. So we need to use this bridge, which we just established, which we just derived. Right? So let me frame it. So we have to use what we just derived. And another thing. Just before we start making this transition, look, what's the direction of the electric field? Since you see electric field is positive, so it means electric field points that way, right? So here electric field 0, then it becomes stronger and stronger and stronger and stronger and stronger. Right? Then another piece of information is given. I wrote, so you see the electric potential at the origin is 0. You remember, we have a freedom to choose a reference point at any point. So in this case, the person who created this, wrote this book, right, gives us this information. Basically, they give us the reference point. So the reference point is at the origin, right? So that's the reference point. Reference point. So since reference point is given, so we will be able to find the electric potential. Otherwise, every time we can get only delta V, change in the electric potential, right? Okay, so now we can start actually solving problem after discussing this. So which formula? Of course, delta V equals minus integral from the initial point to the final point, E, okay, let me write E dot ds, right, in general, like that's what we derived. And now, as I wrote in my slides, so of course we can write it as E cosine theta ds, and of course this is Es ds. I'm still not solving the problem, Es ds. And in our case, S is along x direction. So basically we're going to have a negative integral Ex dx. In our case will be significantly simpler. Formula will look simple. So now I will write, so delta V equals to minus Ex dx. So that's what we need to use in this case, right? And of course from some x initial to x final. Again, basically this formula can be used for any field for, yeah, of course, along the x-axis, right? No restrictions. So we just need to apply this formula for our particular case. So basically, we need to decide which point is going to be our initial point and which point is going to be our final point. And of course, you can use any point as an initial point. But since we have information about the electric potential at point x equals 0, so let's take that point as our initial point. Right? So let me write, so let x equals 0 be our x initial. And then let which point should we take as the final point? Which point should we take as the final point? Again, when we have normal class lectures, right, in the lecture hall, right, I usually try to get that out of students, right? Now it's a little bit more complicated, right? And not usually, most of the time, students give me this suggestion. Let's take x equals 2 as our final point. All the time, basically, somebody gives me this suggestion. But if we take this point as our final point, what are we going to calculate at the end? We will be able to calculate the value of the electric potential at this particular point. But what do we need to get? We need to get the function v as a function of x. So that suggestion usually, I wouldn't say it's not correct. It just doesn't lead us to the to what we need to find. So x equals 2 in this case, it's not a solution. So what do we have to take in order to get the function? We need to get an arbitrary point x. Just completely arbitrary. For example, I will take it over here. I will use probably not red. Here I will put, so x. So let arbitrary x be our x final. Arbitrary. That's what we need to. Of course, if the question was about finding electric potential at point 2, yes, x equals 2 would be our final point. But in this case, we need to take an arbitrary point x. Okay, so as a result, our formula will look, now we can rewrite it, of course, delta V, it's a V at x, at our arbitrary point x, because what delta? Delta, it's a V final minus V initial. And since we pick our final point arbitrary x, so we have V sub x, V at x minus V at x equals to 0, right? V initial, right? And V at x equals to 0, that's our reference point. So this is 0. Right? And the right-hand side minus integral from 0 to x. I'm just rewriting it. Ex dx. And which is area? Which is in area? Right? Which area? Let me continue this line. So it's equals minus area of which curve? Let me label points. This is point O. Okay, let me use different color. Right. This is point O. This is point A. Wait, not that one. Sorry. Not that one. Right. I need to draw this line. Right. So we need to find area of this curve. Under this curve. Right. So that's the area. So our initial point, our final point. So we just need to find area and minus in front. Don't forget about the minus. So it's now I can label. So OAB. A and this point, let me call it B. So area of a triangle OAB. Right? Okay. Area. Of course, it's a minus 1/2 since it's a triangle. Base, this distance OB, it's just x OB. And now we need to find AB times distance AB. So how can we find this distance AB? Right. So in order to write that distance, we need to know the equation of this line. So it's a straight line which goes through the origin. So we just need to find the slope. So it will be slope times x. E equals slope times x. How can we find slope? We can use this point 1. At point 1, the value of the electric field is 1,000. So the slope is 1,000, right? So as a result, the curve, the equation of this curve is E sub x equals 1,000x. Okay, as a result, our arbitrary point x, as a result of this height and this point is just 1,000x. So this point is, okay, this point is 1,000x. And this height is 1,000x. Right. Okay, so now I can rewrite this. You know what? I will start a new line. So this is V. V of x equals, this is 0, and it is equal to this minus 1/2x and times 1,000x. So it will be negative 500x squared, negative 500x to the power of 2. So that's the answer. So I will write underneath. So V as a function of x equals to minus 500x squared. So that's the answer. And now we can plot it, for example. If I plot quickly, all right, so let's say this is V as a function of x. This is x. It's a parabola with a branch down. Okay, let me plot it. Goes through the origin, of course. Something like this. And this is, let's say, point minus, nope. So let's say this is point 1 meter, and this is minus 500 volts. Right. So it's a parabola with a branch down. So again, over here, where students, the point which students don't see immediately, right? Usually, that in this case we have to take an arbitrary point x, right? The rest usually students don't have significant troubles, right? But if the question was about finding the value of the electric potential at a particular point, let's say, for example, point 1, yeah, then we would take that point as our final point. If the question was about finding the electric potential at point 3, for example, yeah, we would take that point. But in this case, we need to do this. Okay, so that's the example which I wanted to discuss. Right. So it just calculate the area, add minus in front.
Professor, I have a question.
Yeah.
So somebody actually asked this in the chat, but I was wondering too. If we decided to just integrate the function like this, we could do that?
You can do that, right? So just some students still not comfortable with integration. They're still taking calculus 1B or whatever it's called, right? So as a result, we don't go into that. But of course, yeah, absolutely. Just here's the function, 1000x integrated. It's trivial integral. Absolutely. You can go with that way. I should have mentioned that.
Thanks.
The integral doesn't give you a negative 500. So the integral doesn't give you a negative 500. It gives you 500x squared. So you got the minus. Never mind.
The negatives in front.
You will get minus.
Oh.
If you try to integrate, okay, you can do that in a quiet atmosphere with a cup of coffee. If you write carefully, write everything. Okay. Again, if you feel comfortable with the integration, yeah, go ahead with that. So let me switch back to the presentation. And there will be a clicker question for you now. And now I checked, and it is polls are in the chat. So you have to scroll the chat up, right? Okay, here, meeting chat. I open it on my computer, and I can see these questions, right? There are 3 of them. So the question number 1. Right. So now there will be a question for you. Let me switch to... So that's the example which we just discussed, and here's the question. Of course, the question is simpler, not like what we just discussed. Again, the same information about the electric field is given, and again, you see we have electric field along x direction only, so one-dimensional case. Again, units volts per meters. It's the same like newtons per coulombs, and you see the graph, straight line, right? X in meters, right? And the question is, what's the value of the electric potential at point 1? At point 1, assuming that the electric potential is 0 at the origin, right? Again, since we have a freedom to take any point as the reference point, so this problem tells us, okay, let's assume that this is the reference point. Again, if you don't give that information about a reference point or value of the electric potential at a certain point, you will never be able to find V. You will be able to find only delta V, right? Every time, that's why every time they give us, okay, let's assume that this is the reference point. Let's assume that that is the reference point. Okay, so in this case, you need to find the value of the electric potential at point 1, and you see the options. And again, the poll is in the chat. At least that's where I found it in the morning. Created, and I found that it's in the chat, right? Meeting chat. Okay, I see you've been answering. All right. So, yeah, it's a normal distribution. What I usually see in the semesters, right? And that's why we need these questions. Again, guys, use the poll, right? Don't just use the chat. But of course, the poll is in the chat. Oh, it looks like somebody changed his or her mind. One option disappeared. Okay, it looks like we almost reached saturation. Okay, some of you believe that the answer is B, 32%, and some of you believe answer is D, 62%, right? Sorry. Usually in the, again, when we had normal classes, right, so, and we use clickers, the answers for this question like create like a twin towers, right? So almost of 50-50, right? 50% believe it's option B and 50% believe like that it's option D. Okay, you're still answering, but we need to start discussing it. All right, so let's discuss. Let's remove one of these. Okay, let's clear your confusion. Right. Yeah, you still. Okay, so initial point obviously will be x equals 0 because they give us that this will be our reference point. Then final point is obviously x equals 1 in this case because we want to find the value of the electric potential at that particular point, okay, at this particular point, right, x equals 1. In the example which I discussed, we wanted to know the function, that's why we picked an arbitrary point as our final point, right? Okay, so of course, in this case, v final, it's the value of the electric potential at point 1. So that is initial point, and that is the final point. And the value of the initial point, the value of the electric potential at the initial point is 0, right? That's our unknown V final, right? So we just need to calculate area under the curve between 0 and 1, and don't forget minus. And what, how many? 28% of students, guys, you forgot about the minus, right? So if we calculate area, of course, it's 1/2. The base is 1, right? Height is 2,000. It will be, the area is 1,000. But of course, we need to put minus in front. So it's not just area. It's a negative area, right? So it's a minus 1,000 volts. Right? And as I said, 27% forgot about this. It happens every semester, right? That's why we need these questions. And 2%, guys, you forgot that the area of a triangle, it's 1/2 base times the height, right? It's not just a rectangle.
So do we just ignore the sign of the slope when we put it in?
Say it again.
So the slope for this line is negative 2,000, right? So we just ignore that negative sign?
But in this case, yeah, you can use the slope, right? You can try to integrate it, right? Yeah, of course, the slope is negative. The slope is negative, but the potential difference is not equal to the slope. It's equal to the negative area. The slope will be in the next bridge, which we are ready to start building. All right, so here the slope, you don't need it. Of course, if you want to integrate, you need to know you need to know the equation of this line. Yeah, you need the slope, right? But you have to be careful with the equation of the line because line doesn't go through the origin. So it's not just slope times x, so you need to also displace it from the origin. So if you want to integrate, be careful. Just sit quietly somewhere with a cup of coffee and write down the integral and integrate it. But in this case, the way we sort of calculate, we just calculate area and, of course, minus in front, right? Or we can discuss integration, how to calculate this using integrals in the office hour. Okay, so minus. Don't forget about that minus. Right. And this question quite often I give on the exam among multiple choice questions because usually it should take like 20 seconds or 30 seconds to answer this question. Right. So next, so the answer is D. All right, and next, the bridge in the opposite direction. So now how can we move from the electric potential to the electric field? Right, reverse. Exactly the same picture. I just copied and pasted like what we had at the very beginning of the lecture, right? And look, do we need to derive something new? I mean, a new expression. Basically, what we need is here. We have electric field, we have electric potential, so all the ingredients are already here. So what do we have to do? We just need to grab this equation and turn it inside out. That's it. So we don't have to derive something new. Everything is here. We just need to turn it inside out. So what does it mean turning inside out? Since this is integral, of course, we will switch to differential form in order to do that cruelty, right? Okay, so now, of course, we need to rewrite it in a differential form. Otherwise, we wouldn't be able to turn it inside out. Differential form, of course, it will be dv equals to minus e dot ds. Right? Because if you integrate it, you will get delta v, and you will get that what we have on the right-hand side. So differential form. And of course, dot product, let's write down explicitly dot product. It's a e cosine theta ds. And theta, it's you see that angle between e and the direction of the infinitesimal small displacement. So e cosine theta ds. And again, like in the couple of slides ago, e times cosine theta. What is e times cosine theta? Look at the picture. This is e, this is theta. If you take e times cosine, you will get component of the electric field along the s direction. You see, you will get just this small component of the electric field, right? Okay? So I can write es ds, of course, minus in front. And now, look, okay, maybe, let me solve it for E sub s, because that's what we want. We want to move from the electric potential to the electric field. So let me solve it for E sub s. So it will be dv over ds and minus again. Right. Okay, now, this s is a completely arbitrary direction. When I was setting up this picture on the first slide, I didn't impose any restrictions. S was completely arbitrary. I can position S along a line along S along this direction, that direction, this direction, any direction. There are any restrictions on the S direction. Okay, so if we have that freedom, let's use it. I can say, I want, my soul desires, and I want to align S direction along x-axis. Why not? We don't have any restrictions. So as a result, I will have E sub x equals minus dv over dx. S is arbitrary. So now I'm getting the formula which will allow me to calculate the X component of the electric field. Now, using the same words, I can say I want align my S direction along Y. And as a result, I will get the second formula, E sub Y equals minus dV over dy. And guess how I'm going to get the last formula for the Z component? In exactly the same way, right? So I will get E sub Z equals minus dV over dz after I align my S direction along Z axis. So we get three formulas. So now bridge consists of three parts in order to move from the electric potential, you see V, to the electric field. And let me ask you this, right? So how come that in order to move from the electric field to the potential, we had only one formula. You see this, one formula. But in order to move back, we have 1, 2, 3 formulas. What's the discrimination, right? This way, one formula, this way, three formulas. How come? And the answer is very simple. What's the nature of the electric field? It's a vector quantity. Vector quantity, right? So we need to find three components, E sub x, E sub y, and E sub z. So we need three formulas. But the scalar the electric potential, it's a scalar function. It's just numbers, right? Of course, we need only one formula. So that's the simple explanation. Okay, and now again, so what? Of course, V must be a function. V function of x, y, z, right? So in order to differentiate. And of course, what's the meaning of dv over dx? It's a slope of, if you plot v versus x, it's a slope with minus. Again, don't forget about minus. Again, it's a very common place for silly mistakes. Right? Don't forget about minuses. Right? So if you have v versus x, some curve, find the slope, add minus, and it's done. Right? Okay. All right, so that's the bridge in the opposite direction, and of course you can write it in a component form, right? And okay, this example I will skip for now. All right, I will skip for now. This it's very simple because it's just application of these formulas, right? Application of these formulas. If you, for example, we will solve a very similar example in our recitation class. All right, so what we have V versus X. And we need to plot, we need to get information about the electric field as a function of x. So three parts here, straight lines. So you need to just calculate the slope, add minus, and you will get the value of the electric field. Here, calculate the slope of this part. Slope is 0 because it's a horizontal line. So the electric field is 0. And here, slope, calculate the slope. Slope is negative. But because of the minus in front, so you'll get the positive electric field, right? So we will solve a similar example in our recitation class. As a result, I decided, so I'm not going to discuss it in our lecture. Of course, you can read it by yourself. It's trivial, right? But again, still, we are going to practice in our recitation classes. Right, and why I'm jumping, right? So because I want to get to my all-time favorite question. I love this question. And I explain why. And that's why I put Garfield with hearts. Right? So what do we have here? We have, you see, plot, electric potential versus x. So first potential is growing, so this is growing, then it's going down, right? Then I will take a electron, right? And position it at the point 2. At rest, and release it. So initial velocity is 0. So we need to answer the question, what does this electron do right after I release it? Answers, kind of option A, it doesn't care, it just stays at that point. Maybe, why not? B, it starts moving to the right with a constant speed. C moves to the right with acceleration, increasing speed. D moves to the left, constant speed, and moves to the left with acceleration. Okay, give it a try. The question is not trivial, at least the way I'm going to answer it, right? Of course, later on, I will give you easy explanation, right? But so here, I'm going to give you an answer which is not trivial, but it consists of trivial steps, and you're all familiar with these steps, right? Okay, give it a try. All right, so I want to see what you're going to get. I want to see the distribution of answers, and then of course I will discuss it. And since the answering consists of several steps, those steps are not complicated. You all know those steps, but you just need to arrange them properly in the right order. All right. So again, the poll is in the same place. It's a conceptual test too. Okay, yeah, I can see it. And I see that you started answering. Okay, now I see that you guys are very smart. Cool. But of course, relative to the previous question, now we have a much broader distribution of answers. And it happens every time. Usually the distribution of answers is basically like a Gaussian curve, right? Picked at the right answer still, which is good, Okay, so we're getting closer to the end. Let me quickly discuss this question, right, before we go. All right, because it will take a couple of minutes, so I will hold you a little bit longer. So let me create the train of thoughts, like a skeleton of this problem. So let me start from the very end. We want to get the direction of motion. Direction of motion is basically kinematics. Physics 1, kinematics. So how can we get direction of motion? How did you get direction of motion in Physics 1? You remember kinematics, 3-level: position, displacement, position, right, distance. Then the second level, if you differentiate that, you will get to the level of velocity. And then if you differentiate that, you will get to the level of acceleration, right? So if, for example, you know information about the velocity, direction of the velocity, that's the direction of motion. No questions. Velocity that way, we move that way. Velocity that way, we move that way. But in this case, initial velocity is 0, and we want to get information what happens with the charge at the initial moment of time. But velocity is 0, so we cannot get direction of motion because velocity is 0. Damn it, right? So what's the next step? If velocity is 0, then you need to dive deeper to the third level. You remember, again, position, velocity, and then acceleration. If we cannot get information about direction of motion from the velocity level, dives deeper to the acceleration level. Let's look at the acceleration, right? Acceleration, of course, we have to be careful because, like, you know, if you drive the car, right, your speed, like, let's say 55 miles per hour, you press the brake slightly, you still move forward, but your acceleration is in the opposite direction. So acceleration doesn't give us direction of motion all the time. So we have to be careful with acceleration. But in our case, acceleration is 0. Velocity is 0. Velocity is 0, right? And if velocity is 0, then only in this case, direction of acceleration give us direction of motion all the time. So it's like in the car. You sit in the car, you started accelerating that way. So it means that you move that way. You started accelerating this way, it means that you move that way. So in this case, only in this case, when the velocity is 0, initial velocity, direction of acceleration give us direction of motion. So as a result, I can, okay, let me press on on slides. All right, so direction, in order to get direction of information about direction, we need to get information about acceleration. Then, how can we get information about acceleration? Newton's second law from the force. So in order to get information about acceleration, we need to get information about the force. Force is electrical. What do we need to know to get information about electrical force? Electric field, F equals QE. So electric field will lead us to the force. And then now we have information about the electric potential, and in order to get information about the electric field, we just established a bridge. So V will lead us to E using the formula which we just derived, right? So that's the problem. That's all the steps that we have to complete in order to answer this question, right? Okay, let me quickly do it. So slope of this curve is negative. dv over dt is negative, right? You see this? And minus in front, so the slope is negative, plus minus. So the direction of electric field will be positive. So direction of the electric field, that way. Then next, direction of the electric field that way, but since the charge is negative, you see charge is negative. So it means that direction of the force will be in the opposite direction. That's direction of the force. Then Newton's second law, mass cannot be negative. Mass is only positive. So if force that way, it means that acceleration also that way. All right, acceleration also that way. And if acceleration is in the negative x direction, so it means that it's also a direction of motion is in the negative x direction. And since acceleration is not zero, because all these are not zero, so it moves to the left with the acceleration. Moves to the left with acceleration. So the answer is E, move to the left with increasing speed. Right, and not many students pick that option. Oh no, just a second, let me, where is? Oh no, actually, plenty. Sorry, I looked at the wrong poll. Some of you used question 3. Okay, so sorry for holding you, right? I thought I would be able to finish it within. Okay, so my all-time favorite question, because we have to use so many steps, but we're all familiar with these steps, but we need to arrange them. Okay, thank you, and see you next time.
Probably in the